In this problem, we have a gear system where A is connected to B is connected to C with a shaft, and then C is connected to D. The angular velocity at A is 10 radians per second at a time of 0 seconds. So initially it's starting at 10 radians per second. The radius at A is 5 millimeters. The radius at B is 10 millimeters. The radius at C is 5 millimeters. The radius at D is 15 millimeters. And the gear A is accelerating at an angular acceleration of 1 radian per second squared. We want to find the angular acceleration at D and the angular velocity at D at a time of 10 seconds. First, let's start with what's happening in A and between A and B. So the velocity on the outside of A will be equal to the velocity on the outside of B. And this is simply equal to the angular velocity of A times the radius of A, which is also equal to the angular velocity of B times the radius of B. Therefore, the angular velocity of B is equal to the angular velocity of A times the radius of A divided by the radius of B. From B to C, we're connected by a shaft, which means that the angular velocity of B is also equal to the angular velocity of C. Now we'll move from C to D. The velocity on the outside of C is equal to the velocity on the outside of D, which is equal to omega C times the radius of C. And substituting what we know from omega C in, we've got omega A RA over RB times the radius of C is equal to the velocity of C, which is equal to the velocity of D, and the velocity of D is equal to omega of D, the angular velocity of D, times the radius of D. Therefore, the angular velocity of D is equal to angular velocity of A, radius of A, divided by the radius of B, times the radius of C, divided by the radius of D. Now we have a relationship between the angular velocity of A, our first gear, and the angular velocity of D, our last gear. This same relationship applies with our acceleration. So the angular acceleration of D is equal to the angular acceleration of A, radius of C, divided by the radius of B, radius of D. If our angular acceleration is equal to 1, then we have 1 radian per second squared times the radius of A, which is 5 millimeters, the radius of C, which is also 5 millimeters, divided by the radius of B, 10 millimeters, and the radius of D, 15 millimeters, which gives us an angular acceleration at D of 0.1667 radians per second squared. Since the acceleration at A is constant, then the acceleration at D is also constant. Now, knowing the acceleration at D, we next need to find what the initial angular velocity of D is. Well, our angular velocity at A was 10 radians per second at a time of 0 seconds. So the angular velocity at D is equal to 10 times 5 times 5 divided by 10 times 15, which gives us 1.667 radians per second. Now, to find our final angular velocity at D, omega final is equal to initial plus acceleration times the time. We can use this equation because we know that we've got a constant acceleration problem. Substituting what we know, our initial angular velocity at D is 1.667 radians per second. Our angular acceleration is 0.1667 radians per second squared, and our time is 10 seconds. Solving this, we get that the final angular velocity at D is 3.33 radians per second.